So good afternoon, ladies and gentlemen. My name is Steffen Bayer from Ariane Group. I'm working for the company Ariane Group, and Ariane Group is the access to space, the success to access to space. And we personally I'm personally working for rocket propulsion engineering and development. And I want to give you a quick overview of our application, which is very challenging. And as some of you know, that we have launched our new product, the Ariane 6 launcher, on 9th of July this year, very successfully. And we had on this launcher a high portion of additive manufacture parts. And so we have now achieved a flight qualification status for additive manufacture parts. And I want to give you some details about these requirements for such a rocket combustion chamber. It's very challenging, so we have very high temperatures of about 3,500 degrees C in the combustion chamber itself, and minus temperatures for H2 and O2. And we have a very, very high fuel consumption of 320 kilogram per second, which is a lot of fuel consumption, and we providing, or this engine here creates a thrust of roughly 4 million horsepower. In the combustion chamber itself, in the hot gas wall near to the throat, we creating very high heat loads of about 100 megawatt per square meter. So you have imagine what or impression what kind of requirements we have in such a chamber. So we are since many years on the way for developing and qualifying AM parts, and we tested here the first rocket combustion chamber in 2019, so a longer time ago, with an all-in-one chamber here. With, you can see here the injector is manufactured by LBM. Also the manifold is manufactured by LBM. And we have the combustion chamber itself. The copper is produced by additive, and the jacket by a DED process. So we have demonstrated that we can use, and then I hand over now to the DED process, which is also in our focus, because it's very interesting for us to have also this kind of DED technique for long-term perspective, for long-term development, for very large components, high-end products with difficult processed materials, and to combine also simple structures and complex features by this technique, by this DED technique called ELA. And we want to have a long-term planning for the introduction of such kind of jacket technologies for combustion chamber. So we're talking now about the DED of a combustion chamber jacket, which is normally used by or normally made by Incus 625 as a reference material. So I hand now over to Tobias Stittgen. He will explain you much better about his beautiful ELA or the 3D DMP process. I hand over now to Tobias.
Yeah, thank you very much, Steffen, for the nice introduction and putting into context what we do with our high-speed DED technology. So before we get into the details of what we jointly developed during the past 2 years, let me briefly explain what all of this is about. So Ponticon is a provider of high-speed DED systems and sensor solutions. And now what we do is we use powder as a feedstock material and melt it by means of laser radiation. So that's easy. It's been around for more than 2 decades already. But there's one major difference in the way we approach it, and that is the way that we melt the powder particles. So on the left-hand side, you can see a picture taken of the powder being fed to the processing zone. And now what we do is we melt the powder while it's still in flight, while it's approaching the part. And in that way, we can achieve significantly higher feed rates on the process that then at the end of the day obviously translate into productivity and precision. So with this kind of technology and systems that we offer, it's for the first time possible to resolve this dilemma in between productivity and precision, because typically in additive, and that's also true for DED, you sacrifice one for the other. With this technology, for the first time, that's not the case. So what we do is, as I already said, we develop and sell those systems. We have a very strong focus on application development. What we're doing here in this context with Ariane, I would still call it a coating process, and then at the same time we also do additive stuff, so we 3D print parts from powder feedstock material. How could such a system look like? Just a brief overview. This is where we started roughly 5 years ago with a very complex, very versatile system for development purposes, and now it's really all about building the systems in a way that they fit our customers' applications. I will explain in more detail what this means in the context of rocket thrust chambers. We're not going to talk about all the technical specs. Just keep in mind, high speed, 2 orders of magnitude faster than conventional DED technology. You'll see some videos in a second. So now with this part, and it seems like the animations aren't working, which is not good. Is there any chance you can remove the video from that slide? Or like put it to the background? Just bear with me for 1 second. He's working on it. Or just keep it as it is and we'll play the video and I'll explain it that way. Come on. Okay, so what we see here is a benchmark part or a thrust chamber that was provided to us by Ariane Group to find out how well the process performs. This is the entire workflow from the toolpath planning all the way then to the actual machine and the process. With this approach, we were trying to find out what kind of angle we could still tackle without tilting the head. So the one on the left still works, the 45 degrees, obviously it's critical, so you would have to tilt the head. What's nice about this is you have collision detection, so it's really all there to make sure you have an efficient setup process. Now, looking at the actual part, and this is a benchmark demonstrator, so it's one of the thrust chambers that Steffen just mentioned, roughly 850 millimeters in height, 600 millimeters in diameter. So it was quite tricky to mount it on the machine when we received it the first time. A lot of weight, high value components, so yeah, it was kind of nerve-wracking, but we could get it done. If you look closely, you can see those small stripes in there. Those are cooling channels that are topped off with some metal stripes. So it's a regeneratively cooled thrust chamber, obviously, to get rid of all the heat that is coming from the inside. The base is made from copper, chrome, zirconium, and now the big challenge is to apply this jacket made from Inconel 6-5 in this case, which adds the required mechanical strength to the part. So what the challenge is to apply nickel base Inconel 6-5 on top of the copper chrome zirconium material. How do we typically tackle this? We start with very small coupons where we just evaluate the material combination. Does it stick to the substrate in the first place? So you see this credit card sized copper substrate on this slide with the Inconel coating on top. Then we can also already check for the microstructure, what kind of density do we achieve, how does the surface look like. So it gives us a very good indication actually before we get to the next step, which is then a small scale part. So now things get cylindrical. We received a small scale sample still without the cooling channels in there. Then again applying the coatings, those thick rings on the outside for material testing purposes. So we had some tensile specimens milled from that. You will see the results in a second. And then up next, I think this is a nice close-up because you can nicely see those the cooling channels underneath. We applied different process parameters, different thicknesses to also check for the residual stresses, because what happens if you apply an Inconel jacket on top of this copper chrome zirconium layer, things would start pulling inward. So it was quite difficult to get it off the tool because there was a lot of stress and also forces pulling towards the inside. And that's actually what we wanted to find out in this first step of process development when applying those larger rings. And then at the same time also understanding how does the temperature develop in the part, because what you want to avoid at all costs is a change of properties of the part that you are working with. So it was really key to make sure that we not exceed a certain temperature in the thrust chamber. So we have to keep in mind we're shining 3 kilowatts of laser power onto this part continuously for many hours. So obviously it warms up, and this is something we have to keep an eye on. Then looking at the interface, doing some cross sections, you can see there's almost no dilution. The layers we deposit, they have a thickness of roughly 100 micron. There's an even better image where the different elements are color coded. So the orange brown stuff is obviously the copper, the green one is the chromium, and then blue is nickel. So you can see, if you look at the scale down here, dilution is less than 50 micron, and there's a very sound bonding in between the material we applied and the substrate, the thrust chamber itself. I just mentioned those tensile specimens. I don't want to spend too much time talking on it, but just to give you an impression, it fails how it's supposed to fail inside the copper section, obviously, which means the interface is sound and has all the required properties, and also the material we applied itself is the way it's supposed to be. We did some measurements on the stresses on the inside, both in tangential and axial direction. What you see that there's the decline the further we get in, which is also a good sign. And then again, the purpose of this is to fly it to space. So it's also interesting to see how the materials perform in like the ambient conditions. So this is at tensile testing at cryogenic temperatures. And getting into another application that we jointly investigated and are still investigating these days is taking this to the next level and not only applying jacket and coatings on these parts, but also do more additive-like structures, like flanges, manifolds, for example, around the machine. Those parts are huge, which means we cannot really put them on the machines that we did the other development with. And for that purpose, we came up with a new kinematic principle where we can accommodate parts up to 4 times 3 times 2 meters in size, so a really huge build envelope, very high speed movements up to 170 meters per minute of feed rate, and then that's obviously a very nice fit for larger applications. This is how the system looks like. It's actually a bit underwhelming to see it on a video, but really impressive in reality. Yeah, I don't know, maybe for scale. So this panel down here, it's 2.5 meters in length and 1.5 meters in width. And then you see the head moving at those crazy high accelerations and feed rates. So this gives a lot of flexibility also for applying features on existing parts, adding stuff on existing components, or just build large components from scratch. What does that mean process-wise? And there's another video running where we deposit a small flange, comparably small, 500 millimeters in diameter, with a cross-section of 20 times 15 millimeters. Again, 20 meters per minute of feed rate, and I would say rather moderate powder mass flow. In this case, only 1.5 kilograms per hour. So the coatings we just saw, we achieved 3.5 kilograms per hour of deposition rate. So there's still a lot of room for improvement. And then for this deposit, and I think the picture doesn't really do justice to the real part. It's 0.5 meter in diameter, 20 times 15 millimeters in cross section, and the deposition time for that was only 2 hours 30 minutes. So if you do this in powder bed fusion, it takes significantly longer, and also if you go for conventional DED, processing time would be significantly higher. And it's not only about processing time, but it's also about the features and the properties that you can achieve by influencing the microstructure. So if you have a high feed rate, you also have very high solidification and cooling rates, which immediately affect the properties of what you deposit. And it's also important to keep in mind that in terms of microstructural evolution, this process that we're talking about is way closer to powder bed fusion than it is to actual DED, because we have those high feed rates and in turn high solidification and then cooling rates. So density of that part 1 close to 100%, that's fine. And some microstructural analysis, we can nicely see the orientation of the grains inside the part. Some stress strain data. I don't want to get into the details of this. Just keep in mind it's as supposed to be, better than conventionally manufactured material, and definitely sufficient for the application that we're discussing. And adding to the crack growth and the stress strain, also some micro hardness evaluations. And essentially this is just the proof that what we're doing here performs the way it's supposed to. So of course it's important to pay attention to this, but I think we could successfully show that what we have does the trick for this specific application. I don't know why the image keeps disappearing, but doesn't matter. To conclude this presentation and not only discussing technical stuff, I think it's really key to also have an eye on the commercial side of things, because somebody has to pay for it and you have to put it to production, and you want to make some money on what you do. So what we see here is a cost split for the coating of that part. And again, so total cost for applying a jacket on this thrust chamber would be around 40,000 US dollars or euros, doesn't matter. And what I really like about this is looking at this first element, which is the machine cost, which in each and every other AM and coating application you see is significantly higher. And for us, it's really all about the material. So the material is adding a majority of the cost. More than 2/3 of the manufacturing cost of this part are a result of the material that we have to utilize. And the machine itself, due to the very high productivity, yes, it's an expensive piece of equipment, that's for sure. But then if you can get a part out of it real fast, that doesn't really matter, because you can keep machine cost at a very reasonable level, and also all the other stuff can be more or less neglected. So I would like to thank you for your application. Feel free to stop by our booth. We have some sample parts with us. We're in hall 12.0, D39, one of the main corridors. And yeah, looking forward to receiving your questions. Thank you very much.
Perfect, thank you. How big are the parts that you have on your booth?
The biggest one we brought is 600 millimeters in height and 450 in diameter.
Okay, nice. A good example then.
Yes.
A reasonable example. We have time for any questions if anybody wants to ask in public, or of course you can go over to Hall 12 and take a look for yourselves and have a look at those parts. But otherwise, that brings us to the close, and we're finished right on time. Thank you very much to all our speakers.
Thank you.
Thank you to you.